quite a few lectures on dynamic programming, and now the topic that I want to cover for maybe the next couple of weeks are greedy algorithms. So if you remember, we talked about this notion of discrete optimization problems. And these were problems of the form, you have some function going from all subsets to, let's say, to real numbers, or sometimes it was all, I'll say, permutations on the set n. Sometimes it was all like, binary search trees on 1 to n, or it was basically parentheses on 1 to n, something like this, going to real numbers. And as we discussed, all of these sets are exponentially large, and often you wanted to find the min or the max of f of s, where s is some element, right? So this was the style of, this is a very common class of problems that you see. Hang on a second, okay. And we discussed, dynamic programming as a sort of approach to solve these problems. So dynamic programming's, even though you finally do recursion, I really think of it at some level as a bottom-up strategy. You can think of it as top-down using a recurrence, but I like to think of it really as bottom-up because in the end, you come up with small problems that you solve and you build up from it. And so in this case, I'd say coming up with the algorithm, with the actual algorithm, is kind of hard. And we discussed this in class many times. Many people had questions about this. How do you come up with it? And this is where, you had to come up with the recurrence. On the other hand, I'd say the proving correctness or the analysis is easy. And what I mean by easy is that once you come up with the recurrence, then it's kind of obvious that the algorithm is correct, meaning that it gives you the optimal solution. And so in greedy algorithms, it's top down, and you'll see that coming up with the algorithm is relatively easy. In most cases, I think many of you would be able to guess what the algorithm is, just as in many of the examples that we did in dynamic programming, many of you would say, oh, you should try this, or you should put this node at the root, or things like that. So you had these guesses, which are pretty natural. And so coming up with the algorithm is not that difficult, but proving correctness ends up being quite hard. So in this case, I think you're not going to ask me how to come up with the algorithm, but you're going to ask me, how do you come up with the analysis? How do you prove something is correct? And this is going to be hard. And so the best way to sort of go over greedy algorithms is to go over maybe a few classic examples, and I will sort of try to prove that they're correct. So a lot of the focus in the next few lectures is really, how does one argue that a greedy algorithm is correct, meaning that it actually gives you the optimal or the best solution? Okay. So we're going to start with a classic problem. So maybe I'm just going to and yeah, okay. Just a second. So spotlight for everything. Okay, done. Okay, so you remember that we saw the knapsack problem, and that was the first dynamic programming example that we saw. What I'm going to give you now is another knapsack problem with a slight difference for which greedy algorithms give the optimal solution. So this is called knapsack with fractional weights. Okay, so how does it work? So just like before, we're going to have these items. Okay, we're going to have these items, these n items. And we have this knapsack. So the knapsack capacity, remember, we call W. And for each of these, we had a value, V1 to Vn, the value, and we have W1, this is the weight. So this is just like knapsack. So, or this is a knapsack problem. So what happens in knapsack is you get to choose some subset of these items. Now what I'm going to do is change it just a bit. Okay. So the problem that I'm looking at is we can pick a fraction of an item. So what you can do is actually, for example, if you're given these items, what you get to choose is you can say, oh, I don't want all of it. I'm just going to take alpha 1 of this, alpha 2, up to alpha n, where these are, of course, in 0, 1. So I get to choose a part of an item, and so I can put these parts into the knapsack. So in the 0, 1 knapsack, which we did earlier, we have to take the entire item. And in fractional knapsack, we can choose a fraction of an item. Okay, does this make sense? Any questions about this? So it's really important that you understand the distinction between this problem and the other knapsack problem. And I'm just going to write down a formulation, more mathematical, and then we can discuss this. So this is how the problem is solved. Given, and these are all non-negative, weights, that is W1, W2 to Wn, values V1, V2 to Vn, and the knapsack capacity of W, solve for the variables alpha 1, alpha 2 to alpha n with the following constraints. So all the alphas are less than Rn1 for all I. So this just means that you have to choose a fraction of an item what we get is that the total weight, so then you get summation alpha I Wi is at most W. Because what this means is if you choose an item, if you choose a fraction of an item, you only have to take a fraction of the weight. You don't have to take the entire weight, right? So you get to save a bit. Okay, and what you want to do is you want to maximize so this is the weight or the knapsack, the weight knapsack constraint. And what you want to do here is you want to maximize alpha I vi, which is the value. So I'll just 1 second, just go over the chats a bit. Okay, yes. I'm sorry. So someone wanted to make, yeah, Jack, you wanted to make an announcement. You can do that in the middle when usually I'll take a break in the middle and just remind me at that point. Just speak up at that point. Oh yeah, it did start, the lecture did start early, but don't worry, I'm going to go over this again. So if you have any questions, feel free to stop and ask me. Okay, let me sort of repeat what I said. So this is the problem. Oh yeah, let me get my page numbers correct. 53, 54, 55. Okay, so let's go back to this. So what is the problem formulation? You're given a bunch of items, just like knapsack. This is a knapsack problem. You have values and weights, and you have a knapsack total capacity. But we get to pick a fraction of an item, which means that for each item, we get to select this variable alpha I between 0 and 1, and you can take a fraction of the item, which means you can pack your knapsack even better. In 0-1 knapsack, which we studied, you have to take the entire item. In fractional knapsack, you can choose a fraction of an item. So one way in this which is formulated is you basically get to choose summation. You have to basically maximize summation alpha IVI. So alpha is the fraction that you picked. Under the constraint summation alpha I WI is at most capital W. Okay? Is this clear? Any questions? Okay, so now I'm going to ask you a question, and we'll see if... Here's my question about this. What additional constraint can be added to make this problem 0-1 knapsack? Okay, so what I'm saying is you can add some conditions. You can add some conditions on this setup, and you can make it a 0-1 knapsack problem. Okay. Do you say alpha I is not equal to 0? Would you say alpha I has to be in 0-1? Or would you say alpha I has to be a natural number? Which of these constraints will make the problem a 0-1 knapsack problem? So let me launch the poll. Yeah, someone had a question? Okay, I think most of you, someone said aren't there only two natural numbers, AI can be 0 or 1? Which is, I mean, I guess that's exactly the right answer. This is the answer, right? So if you add this constraint, which I think most of you got correct, then it becomes the 0-1 knapsack problem. So the 0-1 knapsack problem is more constrained. In fractional, instead of this constraint, you have this constraint, which is weaker. Okay? Any questions about the problem? Okay, then let's move on. So what is the algorithm? Does anyone, maybe some of you have already seen this. What is the algorithm that you would use to solve this problem? Now you can think greedy. You don't have to think in terms of recurrences or any sort of fancy higher level concept. Just think about, what's the first item you would pick? What is the first item you would pick? Someone said the biggest item. The most cost-effective one. The most valuable item. But what is the most valuable? The problem is, suppose the most valuable item is really big, and so you can't even fit it in your knapsack. You could choose the biggest one that doesn't exceed W. Take as much of the first item. Why should you take the first item? Maybe the first item is really, it's really not that, it doesn't have much value. Right? So as I think someone has correctly said, the strategy, the greedy strategy, is pick the item with highest value per weight ratio. Okay, so just to be careful, just to be precise, what we'll do is we'll sort items by VI divided by WI, right? So this is O of n log n time. Once you sort, let the ordering be, pi 1, pi 2, up to pi n. This is just a permutation. I'm just saying when you sort it, pi 1 is the item with the maximum, so I should say decreasing sort. Decreasing sort. So then you get these items, pi 1, pi 2, so on and so forth, all the way up to pi n. Okay, now what? Now what? That's true. Maybe I should call it sigma then. Maybe you wouldn't be as hungry. Yeah, so now what? So you've sorted the items, but how should you, what is the final solution?
Does there need to be I guess not all of the items, there has to be some threshold that some of the items would get cut off at.
Yes.
Yeah. So I guess you would still have to cut off that at that threshold.
You have to cut off somewhere because you can't, because there's a weight constraint. Remember, you still have this constraint. I'm sorry, I can't see where I'm pointing. You still have this constraint.
So would it make sense to before even calculating pi, just cut off at the weight constraint and then calculate pi?
Well, you don't know, right? So let's just say, just to give an example, let's just say there are n items, and I'm just gonna keep it simple, right? Let's just say that the total weight of each item was 1 in each case. Like each of these items was 1, and your knapsack capacity was something like n over 10.
Mm-hmm. Oh, I see, I see. So there's like a
So
selection of like the
yeah,
10.
you could only
Okay.
pick 10 items, but then now I could even make it messier. I could be fractional, right? So maybe this has a weight of 1.3, this has a weight of 1.2, something else is a weight of 0.9, so on and
Okay.
so forth.
Gotcha.
But as someone said, take as much of pi 1 to pi n until w is met, right? So what that means is you take all this item. Now, what is the weight of this item? The weight of this item is going to be w pi of 1, whatever its weight is. So as long as this is less than w, go and pick, you'll get w pi 2. Now, so on and so forth, you'll get to a point where you're picking these, and in this one, you can't afford to pick everything, so you're just going to pick a fraction of it. And the total weight of all of this is w. So at this point, what's going to happen is that, let's just say it's going to look something like this. You're going to pick all of the first item, all of the second item, all of the third item, until you get to the jth item, and you only pick some fraction of it just to fill up your knapsack. But you process in this decreasing order. So the V divided by W is going to keep decreasing. I'm just going to make a simplifying assumption. This is just to help, get rid of notation. I'm just going to relabel so that item 1 is the largest V by W, so on, and so forth. So I'm just relabeling the items 1, 2, 3 so that I don't have to carry this pi around. I mean, it's good to have pi's, but notationally it's a bit of a pain. So I'm just saying you have item 1, item 2, item 3, item n minus 1, item n. And so you have V1 divided by W1 is more than greater than equal to V2 divided by W2, greater than equal to V3 divided by W3, so on and so forth, Vn divided by Wn. And then what you do is you simply set, you're going to choose everything up to some jth item, where maybe you don't choose all of it. So what you get is alpha 1 is equal to 1, alpha 2 is equal to 1, alpha 3 is equal to 1, alpha j is something maybe in between 0 and 1. And then all of these are going to be 0. Right, so all of these are 0. Everything here is 1 up to alpha j minus 1. And alpha j is going to be something that's in between 0 and 1. That's what your solution is going to be. Does this make sense? It's a good time to ask me any questions because I want to go on and analyze this.
Sorry. I came in just to clarify, when you say like alpha 1, you're just implying that like it equals the whole thing?
It means that your choice, because like if you think about how are you going to represent the solution, like let's say you write a piece of code, it's going to output something. So it's going to say, take so much of the first item, take so much of the second item. That so much is the alpha I.
Okay. Is it
So,
just like, is it representing just like the percentage of the item?
exactly. It is
Okay.
exactly the percentage of the item.
Okay. Cool. Thank you.
Or yeah, the fraction, exactly. So it's saying take all of the first one, take all of the second, take all of the third, all the way up to some point. There's some item that you're not going to take all of. And then everything else you just don't take. What is kind of interesting here is that this solution has a very special form. You only take a strict fraction of one item. Whereas it's not obvious on looking at this problem that you should do that. Okay, does that make sense? Okay, any questions at this point? Okay, so I'm a little unsure of whether people are following or not. It's always hard. So, hang on. What I'm going to do is, I'm just going to poll and ask you like, so Are you following? So R is yes, B is no, and yellow is kind of. Y is kind of. So R is I'm following, B is I don't follow, Y is I'm sort of following. Okay? Okay. So, well, I think if you have enough questions, then you're sort of kind of following. So for those of you who are sort of following, this is a good time to ask me questions. What is it that is confusing here? Why
I
don't I? Go
I
on.
was gonna say I do feel like I'm following. I'm just like I'm worried that like there will be something from the first page that like will throw me off again. But up
There-
until like what I'm looking at right now, I feel like I understand.
there's nothing in the first page beyond like some me pontificating on what a greedy algorithm is. As long as you understand the formulation of the problem, I think it's fine.
Okay.
You can ignore like my pontifications. So yeah. So the main point is, if you understand this formulation and this algorithm, mostly things are fine. So now actually, let's go on to what is sort of the main purpose of today's lecture, which is how do you prove this algorithm gives the optimal or the best solution? How do you argue that this was actually the best? Yeah, any thoughts? Induction, okay, maybe, but like, tell me more. Tell me more. Like, how would you proceed? Like, if I said, okay, write down a proof of this fact, prove that this strategy, the greedy strategy, is actually correct. Yeah, so you do have to show the greedy choice is always the best one, but how? Okay, good. So someone says, suppose you have a better approach, prove it's worse than ours. So yes, I like that. I like that contradiction. Contradiction. Okay, good. So I think most of you are sort of kind of going down the right route. Uh, so let's go ahead and let's follow this path. So the reason I want to go over this is to kind of give you a feel, and this is actually a simple enough problem that you'll see the solution on how does one argue that a greedy strategy is optimal. And it's what you do is you take the greedy solution. Okay, so remember we said greedy had a very specific structure. And this is very important when you're analyzing greedy algorithms, that you observe that the final solution that greedy gives you, so this is 1, 2, 3, all the way up to j plus 1 going up to n. So these were all this is how it was chosen. So I'll say that, the alpha values here are 1, 1, 1. This is some alpha j, and this is 0, 0. And everything else up to it was 1. So what we're going to say is, suppose the optimal solution was different. Suppose the optimal solution was different. As someone said, intuitively, there's no way that you could get more money per weight. And it's essentially that intuition that I want to optimize, that I want to sort of formalize. Often what we'll refer to the optimal solution, I'm just going to call it opt. So suppose opt is different. Now, I'm going to make an assumption here, and you'll see that that assumption is not that big a deal, but it does simplify our solution here. I'm going to assume that the value per weight are all distinct. Okay. Now, the reason that I do this sort of is that you could have situations where if two of these had the same value per weight, you could choose a little bit of one and a little bit of the other, and it doesn't matter, right? If there were two items which had the same value per weight, then you could switch between those and it wouldn't change. And so to get rid of those considerations, let's just assume that all of the values per weight are distinct. And if it's not distinct, you can write the proof. It just gets a little bit more messy. Okay, so let's look at the optimal solution. And the optimal solution was different. So what does that mean? So the optimal solution kind of did something where it was different. Okay, so I'm just going to draw this out. Now, if the optimal solution was different, it must be different in some choice up to j, right? It couldn't have followed everything and then done something more, because this is already using up the knapsack, right? I mean, greedy fills up the knapsack. So opt cannot copy greedy and take more. So opt must have chosen less than greedy for some item k, which is at most j. Does this make sense? Greedy filled up the knapsack. Now, opt cannot copy greedy's solution all the way and then take something more. That's just not possible. So opt must have chosen something here less than greedy. Less than greedy. And when I say choosing, it's basically less than weight. Like, it chooses less than the item, not necessarily value. We can worry about that later. It's just choosing less than the item. So I'll just go over the comments a bit. The thing that was previously preventing us from just taking greedy weights was individual weights interfering with other choices. So previously, I guess you mean in the 0-1 knapsack setting?
Yeah.
Yeah, so in 0-1 knapsack, what happens is that there are conflicts because you have to choose the whole item. You couldn't choose part of it. And actually what's interesting is when you see this proof, you'll see how that plays a role. So it's a very good point and exercise to understand, what makes this different from the 0-1 knapsack. Okay, so does this argument make sense? So opt must have chosen less than greedy for some item. So there's some item where it's actually chosen less than what greedy has chosen.
I have a quick question on that.
Yes.
So you're saying it chose like less, let's say like 1 to j. It might have not chosen 2 and 3, so it could theoretically have space for for j plus 1.
Exactly. You're right. Okay. Precisely. So it chose something less over here and something more later on.
Got it. Okay, thank you.
Right. So it chose, but the whole point is it did choose something less in these items, and actually I'll add that. And opt chose some item more for, some item maybe, more than, greater than j plus 1 more. Right, to compensate, it chose something less here and something more later on. And this is exactly what I'm doing, is I'm formalizing a lot of the intuitions that you're stating in the chat. But then that seems like a bad thing, because you chose something whose value to weight was actually less. So it means that, it's a bad choice. And that's exactly what I'm going to formalize. And the reason why I like this problem is that you intuitively understand why the solution is the way it is. And it's just a matter of sort of formally saying why that's the case. Okay, so good. So it means that now I'm going to write this out sort of a little bit more mathematically. I'll say there exists some k less than equal to j, k less than equal to j, such that alpha k, so I'll refer to these as alphas, and for these, I'm going to refer to these as betas. Right? So the choice over here was alpha, the choice over here was beta for opt. So there exists some k where beta k was strictly smaller than alpha k. Right? So that's what's going on. And let k be the smallest such index. So what does that mean? Okay, so I'm going to draw this out. All I'm saying is that, look, there's some index where the optimal choice chose less than the greedy choice. So what this means is I could choose the first choice where opt was different from greedy. And this is a really important concept. I mean, it makes your proofs a lot more easier. So it's saying that if opt is different from greedy, let's go and look at the first place where opt was different from greedy. So before that, opt is doing the same thing as greedy, but there's that first choice. And I'm actually going to look at the first time that opt differs from greedy. So just to draw this out, so here's greedy again. Remember, so we have 1, 2, 3, up to j plus 1 to n. Now let's look at what opt is doing. So I'm going to say this is my index k. So opt did exactly the same thing up to this point. But at this point, it was different. And then j plus 1 up to n. Right? So this is the beta k being less than alpha k. Does this make sense? Now to compensate, there must be some, I'll call it L, where L is greater than K, where beta L is greater than alpha L. It's just saying that because it chose less weight here, there's some item where it must have chosen something more. Maybe it was j plus 1. Maybe it was j plus 2. I don't know what it is. Or maybe it was even j. It could have even been that it took a little bit more of j. It could have taken a little bit more of many different items. I don't know. But I know that there's something where it must have chosen a little bit more. Otherwise, it would not be optimal because it had to fill up the knapsack. Any optimal strategy is going to fill up the knapsack completely.
So could we just compare like all the different ways of like, I mean, I guess this is what we're doing. Like, it just seems like what we just have to do is prove that the greedy algorithm has the most value. And that everything else has less value, right?
Yes.
Okay.
Yes. But what I'm going to show you is that instead of trying to do different combinations, there's even a more direct way of arguing right now. I'm going to sort of do it much more directly. Okay. So how am I going to do that? So I said to compensate, there must be some L greater than K, where beta L is greater than alpha L. Given this information, we will improve or increase the total value of opt. But that's a contradiction. That is a contradiction. It is a contradiction because I assumed it was optimal. There's no way you could improve it. So the very fact that there was some item that was chosen less and some item later that was chosen more is enough to give me the contradiction. Okay, so how am I going to get this contradiction? So let us change opt's solution as follows. So I'm just looking at opt over here. And I'm just going to focus on two items. There's K, where it chose something. And there's some L, where because, so note that beta L is greater than alpha L, and alpha L is at least 0. So beta L is strictly more than 0, which means that there is something where it's chosen something more than 0. Does this make sense? There's some item further on where it's chosen something a little bit more. What I'm going to do is I'm going to shave off some of the weight here and put that in over here without changing the weight of the knapsack. Okay, so I'm now going to remove some of the Lth item and add in the Kth item while keeping the total weight preserved. Okay, so the way I'm going to do this is I'm going to choose, okay, so pick some really small delta greater than 0. And if you're really worried about what this choice of delta is, I'll formalize it. I'll just say that delta is less than the min of beta L and 1 minus beta K. But don't worry about this expression right now. Don't worry about this. Just think of, I'm going to choose something really, really tiny, some very small amount. Very, very small amount. And remove a delta fraction from L. Question: what weight did we remove? Okay, what is the weight of the thing that we removed? Is it delta divided by WL? Is it WL divided by delta, or delta, or is it delta times WL? Okay, I'm just going to launch the poll.
Can you move the sheet up a little
Oh,
bit?
I'm sorry. Yes.
Okay.
I'm sorry. So what weight did we remove? We picked some really small delta. removed the delta fraction from that L, how much weight did we remove? How much weight did we remove? Okay, so it is a third choice, but it's not a majority that got it correct. Although, well, it is the most popular answer, but not the majority. So I want to make sure that I clarify this. So when you pick a delta fraction, what is the total weight? The total weight of this is WL. When you pick a delta fraction of it, you get delta times WL. Delta is like a percentage. So this is the total weight that you've removed if you remove that much.
I think, sorry, because that's what I put, but then I like questioned myself when I saw that delta was greater than 0, because then I started worrying that maybe delta wasn't in between 0 and 1. So like that made me think like maybe it wasn't a percentage. So I'm wondering if other people had that confusion, because
Yeah.
after I picked the right answer, I started questioning myself.
So someone said, is 1 the upper bound? The upper bound on what? On delta? Yeah, delta is a
Yeah, like I think they're like, because
yes, delta is a fraction, right? So
but also have improper fractions. I don't know. That's like
sure,
where my brain's.
yeah, okay, I see. Yeah, no. So it's like it's a percentage of an item, and don't think of like percentage is more than 100, right? So it's like I have an item and I can pick some part of it. So it's some fraction less than 1. It's some fraction at most 1. So again, just to remind you, remember that all solutions look like this. All solutions look like this. So the alphas and the betas and the deltas and all of that are all less at most 1. And as someone correctly said, delta is constrained by how much we took. And so, exactly. So that's why I put in this extra. It's actually even more strict, right? Delta is something which is actually less than, you can't remove more than what opt already picked. We're going to actually see something even more than this. So delta is going to be something really, really tiny. Think of it as like an infinitesimal, just like you do in calculus. It's an infinitesimal. So this is the weight that we remove. We remove delta times WL. Okay. Okay, now here's where it gets kind of interesting. So 57. So I'm going to ask one more question and then we'll take a break. So here's what is the weight that we removed. That's what we removed. Okay, so now let us add in some percentage, fraction of the kth item to get back the total weight. So what am I saying? I'm going to start with opt. I removed some of the lth item, this delta. Now I'm going to add in some of the kth item back so that the total weight is the same. And then I'm going to argue the value went up. Okay? So I removed this much weight. I want to put this weight back in by choosing the kth item. Okay. I'm going to put that back in. And so here's how I'm going to do it. Okay. So I'm going to put in a, let me make this, put in what I'll call a delta K fraction. So I'm just going to refer to this as delta L because this is like from the Lth item. Okay, that's from the Lth item. So I'm going to put in a delta K fraction of the kth item in the solution to regain the weight lost by removing a delta L fraction of the Lth item. Hopefully this makes sense. So we removed some of the weight. Now I want to put in some of this back. So hang on, I'm just going to move this a bit. Okay? I want to put this back in. Put in some of the amount back in. Okay, so you can see all of this. Question: what is delta K? Okay? What is delta K? So the answers are, is it WK divided by WL times delta L? Is it WL divided by WK delta L? Or is it WK divided by WL delta L? Okay? So I'm going to leave this question up here, and this is actually a good point to take a short break. So I want you to ponder over this for the next couple of minutes, and then maybe after a few minutes, then Jack can make the announcement. But I'm going to relaunch the poll, and we'll take a break for a few minutes. And when we come back, we can look at the answer for this poll. Kind of want to make sure that you can see everything that you need to see over here. Yeah, that looks good. Okay.
We can't see the options for the answers now.
I'm sorry. Okay, so I have to.
Yeah. Yeah, that's better. Thank you.
Yeah. Okay. All right. So break for maybe a couple minutes, and then Jack has an announcement to make.
Sorry, clarifying question. Are we expecting to replace all of the weight that was lost by removing the delta L fraction, or just some of it?
All of it, right?
All of it. Okay.
You want to replace, because it doesn't make sense to replace just some of it, right? You might as well just replace all the weight because you want to maximize the value. Like if you have some space left in your knapsack, you want to fill it up as much as possible. I'll just wait for another minute and then I'll let Jack make her announcement.
Would I be able to share my screen to make the
Yeah,
announcement?
so I can. Yeah, so why don't I go ahead and do that? Hang on a second. Okay, so let's pause for a bit, and Jack, you can go ahead and make your announcement. I think you can share your screen.
Okay,
So
cool.
go ahead.
So hey everyone.
Just a couple minutes, yeah.
Yeah, okay. This will be really quick. So basically, I just wanted to share, everyone should have received this email today. Basically, there is going to be a federal funding town hall on Monday from 5 to 6:30 p.m. in the grad student commons. There will be pizza and snacks and refreshments, but basically, here's the flyer. So like, we're basically all getting together to discuss the recent executive orders that have been impacting NSF and NIH funding. And we just want to talk about it and kind of strategize as a community about like what to do. So there's an email that just was sent this morning. It's titled Free Pizza, Federal Funding Town Hall. I encourage everyone to go. I don't know if anyone applied for the NSFG or RFP, but like that's definitely something I'm worried about right now. Yeah, so just wanted to let everyone have that announcement, and I'm going to pop the flyer in the chat as well.
Okay, well, thanks a lot, Jack. Yeah, so go ahead and put the flyer in. I think you can also maybe put a post in Ed on Canvas, and
Okay.
that way all the students will have. Yeah, you just put a post over there. I think then everyone can see it.
Okay, awesome. Thank you so much.
Yeah. Okay, any questions? So I think based on what I see in the poll, where's the poll? There it is. Okay, so, well, participation was somewhat low, but whoever participated did give the right, mostly have given the right answer. The right answer is this, and so why is this the right answer? So if you think about it, the weight removed, as we did earlier, is delta L WL. Now the weight added would be delta K times WK. And you want to make these equal, right? So you want to set delta K WK equal to delta L WL. So delta K is going to be delta L WL divided by WK, which is what I wrote over here. Okay, does that make sense? Okay.
Can you explain that again?
Okay, sure. So look at the Lth item. So we removed a delta L fraction, right?
Yeah, I understand.
So we got delta L WL weight was removed. Now we want to add in a delta K fraction of the kth item so that whatever weight we lost, we put it back in. So you want delta K WK to be equal to delta L WL. Like the weights will be the same. And so then delta K, you can basically solve for this.
Okay, I understand now.
Yeah. So that means, so what happened? We removed delta L from here, added in delta K over here. So that's what we did. So after this change, the knapsack weight is the same, or the items in the knapsack. That weight is the same, right? Because whatever we removed, we added back in. How much did the value change? right? The first question is, how much value was removed, right? Did we remove a delta L VL value? Did we remove a delta K VK value? Or did we remove a delta L VK value? How much value was removed, right? So when you removed the delta L fraction, you removed some of the value. How much value was removed? Okay, so it seems that most of you have seen that this is the right answer. Which again, so you remove the delta L fraction, so you remove delta L times VL value. And so how much value was added? And as you, that's how much value was added. So this is value added, this is value removed. Okay, now I'm going to ask you a question, and I want you to think carefully about it. What would lead to our desired contradiction? Okay, think carefully about this. Is it delta L VL is greater than delta K VK? Is it delta K VK is greater than delta L VL? Or is it delta K VK is greater than delta L WL? Which of these is going to lead to the contradiction? Okay, think about this carefully. I think you should have everything that you need over here. What will lead to a contradiction? What will lead to a contradiction? Interesting. Okay. So things seem to be split fairly evenly. So I'm not going to tell you the answer. Instead, I'm going to say some more stuff and then ask you the question again. Okay. So we started from opt, which was supposedly the best possible solution. We started from opt, which was different from greedy, right? So we started from opt, which is different from greedy. So opt, we changed opt by removing delta L VL value and adding in delta K VK value. We would get a contradiction if opts, if the solution, if the value went up or increased, right? That would be a contradiction because we assume that it was the best possible solution. Now I launch my poll again. Now I launch my poll again. Okay, the overall signs of the poll are pretty good. It's pretty good. Okay, good. So I think most of you see that that would lead to a contradiction. Now I'm going to prove that is the case to you. So let's look at delta K VK minus delta L VL. So by our formula over here, we know what delta K is. So delta K is, so we get WL divided by WK times delta L times VK minus delta L VL. So I'm just going to take this delta L out in comp, and I'm going to say it's WL VK divided by WK minus VL. Okay? Now I'm just going to take out.
Sorry, shouldn't that last one be VL instead of VK?
Thank you.
Yeah.
Thank you. Yes. What I get over here is VK divided by WK minus VL divided by WL. Why am I done? Why am I done?
Why is it delta L divided by WL, like the last formula?
Oh, I just pulled out WL. Oh, I'm sorry. Did I mess something up over here? No, I did mess something up over here. There you go. Sorry about that. Yeah. Okay. Why am I done? What do we know about K and what do we know about L? Remember, we said that L was later on in this list, right? Because we started with opt, we said that there was, because it was different from greedy, there was some K for which it was less than greedy, and there was some L later on where that beta value was more. So there was some item that was earlier that was less used, some item later that was more used. This earlier item was K, the later item was L. What did we sort by? We sorted by weight per value per weight, exactly. So we already sorted by value per weight. And so this is greater than 0 because k is less than L. Right? And that's the contradiction. And so to sort of trace this all the way back, what this means is opt could not be any different from greedy. Because if opt was different from greedy, there was some item that was less used and some later item that was more used. And we can then change the opt solution and improve it, and that would be a contradiction. Okay? So that's the whole shebang, the entire argument together. Any questions about this? Have you mostly sort of followed? So, I'm going to relaunch the poll. Red is, yes, I mostly followed. Blue is, I have no idea. And yellow is, well, I sort of kind of followed. Okay, so mostly it looks like things have gone well. So good. So this was an example of a greedy algorithm and the analysis. And again, in this case, the greedy algorithm was not that difficult to come up with, but the analysis requires a little bit of work. And your intuitions were all pretty accurate. You all had the right idea. What I was trying to show you was how do you formalize that intuition and write it out in a sort of formal way so it's a proof, it's a formal argument. And the best way to understand this better is to see more examples of this. So I want to take another classic example. And this is something that you might all appreciate and understand. Certainly those of us in the university really go through a lot of this. This is lecture scheduling. So here's how it works. There are a set of lectures, each with a start time that I'll call SI and end time EI. So you can just think of this as times in a day, right? Now all of the lectures are happening the same day. And so you have these lectures S1, E1, S2, E2, SN, EN. And I'll say lecture I conflicts with lecture J, and SI is less than EI, obviously. If SI, EI, if the intervals SI, EI, and SJ, EJ overlap, right? This just means that you cannot hold both lectures in the same place. Pretty obviously. Problem: maximize the number of lectures that can be scheduled in a single room. Right? So that means that over our conflicting lectures cannot be scheduled. That's the rule, right? So you can put in any bunch of lectures that you want, as long as someone said you're getting undergraduate algorithms flashbacks. I mean, I guess that's sort of the point here, although this is supposed to be a graduate algorithms course. So if you've already seen this stuff in undergraduate algorithms, I don't know if I should be doing more of it. But anyway. Okay. Right? So you want to maximize the number of lectures that can be scheduled in a single room. Now you might think, well, okay, this looks like, this is a real problem. But let me give you actually an even more compelling example of this. Instead of lectures, imagine a compiler, and this was the lifetime of a variable. So there's a variable that has a start time and end time with respect to lines of code. Like this started at like the 11th, instruction, ends at the 100th instruction. This variable is alive from one instruction to another. Now, instead of maximizing the number of lectures, you want to maximize the number of variables that can be stored in a single register, right? Because if you have two variables whose lifetimes, this is like a lifetime of a variable, don't conflict, you can actually store them in the same register and you can save on register space. So this lecture scheduling problem is actually also used for compiler optimization when you're trying to store variables in registers. Okay, so just to give you another picture of this, you could imagine this is S1, E1, S2, E2, S3, E3, maybe S4, E4. I'm just using parentheses so that you see the beginning and the end. Yeah, I could also use some other tags. Exactly, I could do S5, E5, so on and so forth. Okay, so does anyone remember what the greedy algorithm for this problem is? What should you do? What is the optimal thing to do? Yeah?
Wouldn't you need to like find the smallest like lecture lengths to like
Okay.
get the most lectures into like because if you did S4 and E4, you pretty much can only fit that one lecture in there.
If you did S4 and E4, right, then you would only do that.
Yeah. And so, but the goal is to maximize the individual amount of lectures or just to maximize like that that it's completely used for lectures the entire
That's a
time.
good question.
Yeah.
I'm not maximizing time. I'm maximizing the number. One could also ask about maximizing time, and that would be a different problem. Maybe I should put that in the homework. Good question. Good question. Yes. So someone said earliest end time or latest start time. Okay, why? You have to be a little careful about doing the one that is the shortest lectures. Like that might be one instinct to just start with the shortest lectures. But sometimes, let's just say you had a very long lecture, an incredibly long lecture, but it started before everything. Then you might as well put that in, even though it's actually much longer than some other small ones. And sometimes the problem with small ones is the small ones might, you could have a situation like here's a really pathological situation, but here's a very small lecture that actually just conflicts with everyone. Like you could have a bunch of lectures over here and a bunch of lectures here, and then there's this small lecture here that just happens to conflict with everyone. So you don't want to use that small one. Okay, so I think, what someone put in the chat, earliest end time means most time available after, so for more space for lectures, and that's the intuition. Now that's interesting because that would at least take care of this example. If you did the earliest end time, you would definitely schedule this one first, and then you would have the others afterwards. And indeed, that is exactly the right answer. So it is the earliest end time. So let me write out what the greedy algorithm is. What is the greedy algorithm? Sort in increasing order of end times. This is exactly as someone said. And so I'll say, while there are lectures remaining, we'll schedule the first remaining lecture. And by first, I mean, again, this is by first by the end time, right? Because you've sorted. You schedule the first remaining lecture, and then you remove all lectures conflicting with this lecture. And you can think about it, you have to do it a little carefully. You can do it in O of n time. So in O of n log n, so you sort by increasing order of n time, and while there are lectures remaining, you schedule the first remaining lecture by n time because you already sorted, and then you just remove everything that conflicts with it. So if you had something that was conflicting with this guy, you just remove all of these because you can't schedule those, and then you just repeat. And then you just repeat. Okay? So this is the optimal greedy algorithm. And what you'll see is that the argument to prove this, and again, so we have to do this sort of idea of trying to understand why this is optimal. And so the intuition hopefully makes sense, right? When you schedule the one with the earliest end time, it sort of creates the least conflicts. But you have to be careful because there are other greedy strategies that make sense, like choosing the shortest lecture, that actually don't work. So to prove that this is correct, we need to be a little careful. And so I'll write out the argument, and you'll see that this argument is actually significantly easier than the previous one, but it's actually a very nice argument. Okay. And so let me prove a small claim, a statement. I'll just say that there exists an optimal scheduling of lectures that picks the lecture with earliest or first end time. So I'm just saying, all I'm saying is if you look at that very first choice, there's always an optimal scheduling that uses that first choice. That's all I'm saying. Okay? So let me give the proof.
Sorry. I have a question.
Yes.
So
Yeah.
I'm just like looking at this. So like, what if you have, I wish I could draw it. Basically, what if you have a lecture, like what if you have a really long lecture that starts, let's say it starts at 7 a.m. and ends at noon.
Right.
And then you have another lecture that starts at 9 a.m. and ends at 10 a.m. That this approach would pick that lecture that starts at 9 a.m. and ends at 10 a.m., right?
Exactly.
So, okay. So this,
let me draw that. I think that's a good example to draw. Okay, so okay, fine. Let me draw that. So here's time. So your first example was you have 7 a.m.
Yeah.
and then noon.
Yeah.
And then you have this other lecture which started at 9 a.m.
Yeah.
and ends at 10 a.m. or?
Yeah.
Okay. You're right. This strategy would pick this lecture, not that.
Okay. Okay, so this one, like, definitely, like this would not optimize for time at all because, like,
It is not optimizing for time.
Yeah, yeah. So, like, these are definitely going to be distinct kind of approaches. Okay.
That's a good point. So maximizing the number of lectures is different from maximizing the amount of time that is used.
Okay. Yeah.
And I think it is a very good question as to how you would maximize the amount of time.
Yeah. Okay.
Right. Yeah. Okay. So again, I repeat, optimality means the number of lectures. Optimality is the number of lectures. Okay? So let me give out this proof. So we're at about 9:20 years. So maybe another 5 minutes or so, because I think I did start somewhat later. So I think I do have some time. Okay. All right. So what is the proof of this? So for convenience, let S1 E1 be the lecture with the first and I'm just relabeling so that E1 denotes like the one that ends the first. Okay. Now suppose the optimal scheduling did not choose S1 E1 because okay, so then what this also means is there must be some lecture SI-EI in the optimal solution that conflicts with S1 E1. Okay. Why? Why must there be something in the optimal solution that conflicts with S1 E1?
Is it because the first choice is not always the best choice?
No, that's not why. Okay, there is a comment that says otherwise you could just add it in for free. Exactly. If there was nothing in the optimal solution that conflicted, well then you could just add S1 E1 and then you would improve. You would increase the number of lectures by 1. So the very fact that you started with an optimal schedule means that you must have something that conflicts with S1 E1. Okay, so you have S1 E1. And you have something that conflicts with SI-EI. Okay? Let SI-EI be the conflicting lecture. Remember, this is not the only picture. The picture could also look like this. Right? The picture, well, okay, so sorry, let me leave this here. Let SI-EI be the conflicting lecture in the optimal schedule. This is exactly just what I said. I just repeated that. Question: can EI be less than E1? There's yes. Blue is no. There's 2 options. True, false. Okay. Okay, good. So the answer is no, because that's by definition. I said SIEI is the lecture of the first n time. Okay. So what we have is there's a conflicting lecture. Now what I'm claiming is the only lecture that conflicts, the only lecture in opt, right? So I'm going to refer to this optimal scheduling as opt. The only lecture in opt that conflicts with S1E1 is SIEI. So I'm saying that there's only one lecture that actually conflicts with S1E1. Now, why is that? Consider any other lecture SJ, EJ in opt. Now note that SJ must be greater than EI. Like it has to start after this lecture, or because any other lecture in the optimal schedule cannot conflict with SIEI. So if you look at any SJ, EJ, either SJ is greater than EI, so that's SJ over here, or it has to end before SI. Either has to start after this lecture or end before this lecture. But this is not possible, right? This is not possible because E1 is the lecture with the first end time. So the only possibility you have is that every other lecture in opt is starting after the end time of EI. And so SJ is greater than EI, which is greater than E1 because this is the earliest end time. So all other lectures in opt start after E1. They do not conflict with S1E1. So we can remove lecture SIEI and add lecture S1E1. We have a non-conflicting schedule here, and the number of lectures stays the same, right? Because I removed one lecture and I added in one lecture. So I removed one lecture and added in one lecture. A drawing would help. Okay, so let me sort of draw this out. So the idea is this. So let me go back and maybe explain this. What we have is you have S1E1. Couldn't you choose either one? Yeah, you're absolutely right. You could choose either one, and that's why I'm just saying there exists an optimal solution that picks this lecture. What this means is, even if there was an optimal solution that didn't do Greedy's choice, there is an optimal solution that does do Greedy's choice. So the important thing is to say there's always something that matches Greedy's first choice. So I'll just draw a picture of this. So S1E1 is here, and then we said SIEI is here. And I'm just saying that for every other SJ, EJ in the optimal scheduling, SJ is more than EI. That means that it always has to occur afterwards. There is no lecture that could start before this lecture. Because if it started before, it has to end before. And that would mean that would violate the fact that E1 is the earliest end time. So everything starts after. So I could either pick this or pick this.
Sorry, so you're saying that like for it within, okay, so opt being like in this optimal solution where we've already decided that nothing's overlapping, then
Yes.
SJ has to be greater than EI.
Correct.
Okay, so I think that's where I was getting confused is like, well, surely there can be classes that like overlap. But you're saying like, no, if we have the solution where nothing's overlapping.
It's all the other lectures in opt. I'm only looking at the lectures in opt. There could be other lectures out there. Someone asked, what prevents a lecture from starting between E1 and EI and ending after EI? You mean something like this? There could be such a lecture, but it could not be in the optimal solution because the optimal solution is non-conflicting lectures. So all I'm doing is just changing the optimal solution. Right? So we can remove this lecture. We have a non-conflicting schedule. The number of lectures stays the same, and we have added S1E1, which means there exists an optimal scheduling of lectures that picks the lecture with the earliest end time. So I want to sort of, reiterate this point. The idea for proving all these greedy algorithms is you start with an optimal solution and you try to modify it. You play this game of modifying it to make it look more like greedy. And either you get a contradiction or you say, oh, you know what? I could match what greedy is doing. So what this says is there is a solution that matches greedy's first choice. Now we're out of time. So when we come back for the next lecture on Tuesday, I'll show you that with this and sort of basically an induction argument, you can show that the optimal solution can be shown to match greedy. I want to emphasize there do exist solutions that are not greedy, just as in this example. As someone pointed out, you could either choose S1E1 or choose SIEI. There are solutions, optimal solutions that are not greedy, but greedy is an optimal solution. And sort of that's the point. Okay, so let's end the lecture here. So thank you all for adjusting and allowing me to take this online. And so on Tuesday, I will see you all in person. I think there were a couple of people who had questions they wanted to ask me. So I'm just going to ask you to stay behind, and then we can handle those questions. All right. Thank you, everyone. And so we'll end here.